Now we're going to take a look at sensitivity analysis. That involves either asking how much can the coefficients of the objective function change, or how much can the right-hand side of a regular constraint change. Those constraints would be of the form, let's say, you have positive values for M and N, and a positive value for Q. How much could Q change? That's another question of sensitivity analysis. It might be something about how many hours of labor are available, for example. Our first question with how much can the coefficients of the objective function change? I wrote in the previous example, I'm going to link that previous example in case anybody has jumped to this question, to this video, and did not see the previous example, because that previous example is going to lead to what we're doing here. So I'm going to link that. Okay, so if we solve this for y, we have the slope of negative a over b here. Change one of these coefficients, you're changing the slope. And our question is going to be, how much could it change by? What range of values could it be within and still have the same point on the feasible region, the feasible set, be the one that's producing the maximum? In that previous example, this point C, which had the coordinates 120, 60, that was producing the maximum when we had that P was equal to 10x plus 15y. Now, since I'm talking about slopes here, let's do a little pause, just a moment. Produced a maximum value of 2100. And let's see here. When it hit point C, i.e. 120, 60, at that intersection, just a moment. All right, so in our consideration of these slopes, I could make the slope so that it matches up with the slope of connecting points C and D. And still, although that would change the maximum value, it would allow for C to still be producing the maximum. In fact, both points C and D would. Or I could make the slope of the objective function match up with the segment connecting points B and C. This would also change the maximum value that's being produced, and yet still have the point C, in fact, any point along the segment from B to C, produce the maximum. So, focusing on the slopes, focusing on the slope of the objective function with this unknown value of C, and we're focusing on the slope of the two constraints that we're intersecting to produce that previous maximum at 120, 60. All right, so first of all, we're going to consider x sub 1 to be x and x sub 2 to be y, and we're going to solve for y. in the objective function to find out a formula for that slope. Subtracting cx1 from both sides, and then dividing everything by the coefficient of y, i.e. the coefficient of x sub 2, dividing everything on both sides by 15, we see that the slope of the isopropyl line is negative c over 15. Now I'm going to get the slopes of the two regular constraints. For the first one, we're going to find that its slope is negative 1/4. And if that negative 1/4 equals the negative c over 15, I can get that a number of ways, including cross multiplication. We get that c is 3.75. Let's take a look at what that does. Okay, c is 3.75. It's going to become parallel to the segment connecting C and D. Now, let's do similar kind of work. Oh, you could not see that. Sorry about that. Start that again. Go. Right about the time that it reaches C, we've got a lower value for Z, what we're trying to maximize, than what we had in the previous example. That's okay because C is changing. So similar work for the other place that things were, the other line that we had intersecting at the point that previously produced the maximum. That came from the second regular constraints. Okay, so if we solve this one for x2, i.e. thinking of x sub 2 as y, here's what we get for the slope. We get that its slope is negative 2, and solving where that equals the slope of the isopropyl line, negative c over 15 equals negative 2, tells us that c equals 30. Let's see what that does. C equals 30. We can see that that's parallel to the segment connecting C and D. Let's move it kind of slowly. Let's see here. Try to give it a bigger value. See what happens now. Go even bigger. And it should be becoming clearer that it's parallel, but right around here, getting that to match up with C as one of the things that it encounters. Okay, so what that tells us, because it could go as low as 3.75 and intersect this line segment here. In fact, it would be parallel to it. and as high as 30. And of course, 3.5 is less than 30. Then what that's telling us is that C has to be between 3.75 and 30. It can be exactly equal either one of those, because we're seeing that the line would actually, for a particular value of Z, meet up with the segment connecting both our original point and the other endpoint of that segment. So our value of 10 that we originally had for the coefficient of x sub 1, or just x, that was 10. That's in between these two values.